He usually does a good job. I think the biggest problem with Zotero is sometimes it doesn't find the date or the author name, and you might actually have to look at the website to figure out the date and the author name, because Zotero can't figure it out from the website.
So if there's no author and...
Yeah, but most of the times when students think there's no author or date, there actually is an author and date.
But if it really don't have one?
If it really doesn't have it, then it doesn't have it. That's fine.
So what do we write?
I think no date is ND, isn't it?
Yeah, but then what about like our bibliography?
Yeah.
That part, they have like normally it's name of author, date, and blah blah blah.
Yeah.
But then if there's no author, what do we write? Is it a website title or the name of the website?
I'm not sure. If you're asking me, is it the name of the website or
title or
the title of the article?
Don't you need both in the bibliography? The name of the website and the URL?
Yeah, but not the first part.
Ah.
The one before the note.
I don't know.
Will you check when you mark our...
I'll tell you what's more important for me for the reference. The in-text citation. Like, I really don't like if students have bad in-text citation. Like, if I'm reading something and then the in-text citation is like, physics class. I'm like, well, don't do that.
If it's the website title, you can't change that.
Yeah. Like, Zotero will do a fine job of making it. And the only problems with Zotero is the author and the date. Okay? So if your Zotero is not giving you an author or a date, have a quick check to see if there is one. And if there's not, that's fine. That's fine. What's most important for me for the reference is the source is a good quality. Okay? So if I'll look at the reference, and if I see something like, you know, whatever, like MIT physics notes dot or slash Professor Smith or something like this, I'm like, yeah, that's fine. This is some lecturer's notes from a reputable academic source. Okay? But if I see something like howitworksblog.com slash user 123 smiley face, I'm like, no. Okay, because you get what I'm saying? Like, for me, the most important thing is what the source is of. So if it's of good quality, and the safest thing would be to use a book or to use the notes of a professor from a university. So if I see a .edu means American University, like, that's fine. I'm not even going to check it, you know. If I see something like you're referencing like A-level physics book or whatever, I'm not going to check it, okay. If I see like howitworksblog.com slash hashtag Twitter or whatever, I'm going to check it and probably say not good, okay. That's most important for me. Yeah? Okay. I think this, maybe the other two, who are we missing? We're missing Bruce and Darius. And Sham. Sham's not here. Yeah, we'll just have to start without them.
Oh yeah, teacher, for my tables, I put in U, V, and small and capital M. Do I need to mention like what does the letters stand for?
Oh goodness, somewhere, yes, you need to mention it. Of course. Because the reader won't know what it is.
Okay.
Yeah.
Even the slope?
Yes. Yeah, you can't just use a letter without at least once saying what it is. Even if you just in one sentence say the slope M is in the table below.
Can I just put it in point form like here?
Nah, that looks ugly. No, that's ugly. Put in a sentence. Yeah. Okay. Physics, atoms. Great. Okay, let's continue. Oh, sorry. Probably should plug it in. It would help in getting the signal to the TV. You okay, Wilkie?
Yeah.
Oh, what's wrong with you?
I need water.
You need water? Do you want to go get some?
No.
Okay.
No, no.
Not now, okay. Are you ready, guys? She complains about something?
No.
You sure?
Push.
Okay, there you go. Einstein's equation.
I know this.
What
It's
is it?
Famous equation, right?
Oh, very famous. Very famous.
Right. MC squared.
Yeah, that's the one. That's the one, yeah. Exciting.
Yeah.
You will discover what it means.
No.
No.
I just heard it.
Yeah, you will discover its meaning now. Okay, Einstein's equation. Let's have a look. Okay. Now, because the mass of a proton and a neutron are so small... Is that the door? Do you mind getting that, everyone? Thanks. Who's it going to be?
Bruce.
No, Sham Sham.
Oh, okay.
We're all wrong. Darius. We're all wrong and disappointed. What happened to you, Darius? What happened to you? Nothing. Okay. Because the mass of the proton and the neutron they are so small, we don't use kilograms because kilograms is too big for a proton or a neutron. Instead, we use a smaller unit of mass, not the gram, because even a gram is too big. We use something called an AMU, an atomic mass unit. The symbol is U or AMU, and the value of an AMU is this. Now, the good news is this is actually on your Casio calculator. It's one of the large constants towards the end, like 39 or something. What number is it?
AMU?
Or just U?
Is it 17?
17? Correct, yeah, 17. Yeah. So,
This number is given on the formula rule.
it is, but if you have it on your calculator, it's
I
easier.
mapped it.
That's okay, fine.
You?
Oh, it's not on that, is it? It's number 17 on this one. It's on it? Wonderful, wonderful. Constant 17. Okay, so if I'm using AMUs, then I can say the mass of a proton or a neutron is about 1 AMU. Now, it's not exactly 1 AMU, but it's pretty close to 1 AMU. That's worth noting. Got that? Yeah? Did you do this in chemistry, or this is not a chemistry topic?
This is not.
No. Continuing. So, here's a nuclear reaction. Cockcroft and Walton did this experiment about 100 and a bit years ago. Very simple experiment. What they did was they took a proton, which is H1, and they fired the proton at a lithium-7. And the proton and the lithium-7, it broke into 2 heliums. Okay, now is this equation balanced? It is, because how many protons have I got on the right? 4, and on the left, 4. How many nucleons? 8 and 8. So it's balanced, okay? Yes, it's balanced. Seems to be. Now, let's have a look at the masses, okay? This is the mass of a proton. I said it's about 1 AMU. It's actually 1.007 AMUs. The lithium is 7.016 AMU, and the helium is 4.002 AMU. Now, what I want you to do, can you tell me, add up the mass on the left and the mass on the right. Tell me what each is. So, what's the mass on the left, if you can add this and this?
8.023.
For sure?
8.00. Oh, it's different.
Isn't it?
Yeah.
If you get the mass on the left, and the mass on the right, you get two different answers.
What?
In fact, the one on the right, is it bigger or smaller than the one on the left?
Left is bigger.
The left one is bigger, the right one, the total, is smaller.
Yeah.
Okay, so what is going on? Mass does not just disappear, or does it? Okay, so you might think there's something missing in the equation, but there's not, because it's balanced, so there's no missing element. But the total mass here is less than the total mass here. So what's going on? There must be something missing from the equation. So anyways, why did Walton do this experiment? Well, Walton did not decide one day to do this experiment. You know, it's not like Walton and Cockcroft woke up and said, let's fire some protons at a lithium, see what happens. Okay, they were actually doing an experiment to test an equation that they read in a paper published by Einstein. See, they were trying to, just like you did an experiment with Newton's second law, they were doing an experiment with this new equation that Einstein published. They wanted to prove Einstein's equation. Einstein predicted that when atoms combine in a nuclear reaction, some of the mass appears to be lost, but in fact it's not lost, rather it's converted into energy. This is what Einstein predicted. And he predicted it by a formula. Einstein said that the energy produced will be equal to the mass lost times c squared, where c is the speed of light. Thank you, Ravon. Let's see who this is now.
Shamsha. Oh, Bruce.
Bruce!
Where's Shamsha?
Gone. Converted into energy.
Shamsha.
So, more commonly written E equals mc squared.
Lost mass and light.
Lost mass and gained energy.
What is C equal?
Speed of light.
What is the M?
Huh?
The M.
The m is the missing mass, the mass that was lost in the nuclear process.
C by 10 to the 8. Right?
Yeah. Or rather 2.997 or something. Oh, now this has to be. It couldn't be anyone else. What happened to you, Shamsham?
I was the first bus.
Why did you miss the first bus?
Yes.
Why? Were you and Bruce on the same bus?
No.
You walked. Then why are you late?
On the road.
Interesting. Okay. Now, this actually gives us a very interesting realization. So what does the conservation of energy say?
Energy is conserved.
Energy is not created nor destroyed.
Yeah.
Okay? At the beginning of the experiment, you didn't have this energy, and at the end of the experiment, you lost the mass and gained the energy. But energy is not created or destroyed, it's only converted. But where did the energy come from, according to Einstein?
Oh,
From the mass. Therefore, the conclusion is, mass is a form of energy.
Oh.
Yes? Very big deal.
Yeah.
Yes, very big deal. So heat is a form of energy. Electricity is a form of energy. Chemical energy, sound energy, these are all forms of energy. Now, apparently, mass is a form of energy.
Why did they predict that mass is a form of energy? Why not energy is free?
Yes, like, why was the conclusion that mass is a form of energy and not that simply energy just was created? Because it's hard for me to emphasize how important the rule is that energy is not created or destroyed. Like, it's like the most important rule in physics ever. The reason actually is, or let me actually put it this way. Why is C in this formula? Like, really think about this. Really think about this. If some mass turns into energy, what on earth has that got to do with the speed of light? Like, why on earth should speed of light have anything to do with this formula? Like, this is just sitting here and it turns into energy. What has that got to do with the speed of light? Like, why should that even be in the formula?
Conversion rate.
Oh, because it's a big number. Yeah, but why the speed of light? Why not just a big constant? You know, like, why is it the speed of light? Why isn't it just some big constant? You know?
The energy moves in that speed.
No. No. And this is the thing. The reason Einstein came up with this formula was actually originally studying the behavior of light. And when he was studying the behavior of light, this formula appeared, E equals mc squared. So actually this formula is a result that the speed of light is a constant in the universe. Okay, so because the speed of light does not change, it's the same for everybody, everywhere, at all times. It actually, that produces this formula. That's why the speed of light is in it. Now you might say, how could that produce this formula? It's complicated, but it does. Yeah. When I say the speed of light is the same for everybody, I mean everybody, including the people who are moving. Yeah, now like just really think about that. For example, if he is walking to the window at 2 meters per second and I'm sitting here, I'll see him walking at 2 meters per second, right? Now if I'm also walking to the window and he's walking to the window, will he look like he's going faster or slower to me, compared to me? Slower, yeah. Now imagine he's walking to the window and I'm walking away from the window and I measure his speed with, like, you know, a speed gun like the police use. Will I get a bigger number or a smaller number? Bigger. He's walking to the window and I'm walking away from him, and as I'm walking away I'm measuring his speed. Will that be more or less than 2 meters per second? More. Okay. What's weird about light is the speed always looks the same for everybody, even people are moving towards the light wave and people are moving away from the light wave. It's that constant. It doesn't change even if you're changing.
What does the speed of light have to do with us walking?
I'm trying to draw on a comparison. So imagine I replace him with a light wave. Okay? If I'm walking towards the light wave, I see it moving really fast. If I walk away from the light wave, I see it moving at the same speed. That's crazy, isn't it?
I don't know.
Exactly. All right.
Other electromagnetic waves.
They're the same. It's not just it's for any electromagnetic wave moving at light speed. Its speed is always the speed of light compared to anybody who's moving at any speed, which is really strange. Yes, it is. Yes. Are you doing this on your presentation? Oh, you're doing this on your presentation. The wormholes. Ah, yeah. You can tell us about it next week. Okay. You don't? Ah, shame. Okay. Continue. You got Einstein's formula. So let's calculate how much energy that is. Okay. So can you tell me what the missing mass is? Calculate how many AMUs are missing exactly. Let me open up the calculator as you do this. Dong dong ding, come on.
0.019.
0.019?
Yeah.
Yeah, that's how much is missing?
Yeah.
Right, so let's see how much energy that is. So, no, wait. What is the mass that's missing? 0.01 AMU. You need to convert that back into kilograms before you can calculate anything. 27 multiplied by c squared. So, I'm sorry, what did you say it was? 0.019 times, What's the constant number? 17?
17.
And what's the constant for C? C0, what's that on the calculator?
3 by into the...
But I want it exact.
28.
28. Yep. Alright, MC squared. So how much energy do we get? We get this much. Now that's a lot.
Yeah.
I know it doesn't look like a lot, but for the size of the atom, it's a lot. Okay, because what's the mass of an atom? 10 to the what?
10 to the minus...
What scale? 10 to the minus 27.
Yeah.
That's the scale it's on, to the minus 27. This is to the minus 12. That is many, many, many times bigger. Okay, if you want to really get the comparison, we should convert this into electron volts. What number is that? 23, isn't it?
9.
Oops. That's 17 mega electron volts. Now remember, 1 electron volt is 1 electron potential energy when it's in a 1 volt field. So you're saying that the energy created is 17 million of these. And that's the scale you're talking about. So if you have an atom, it's like the energy it makes is millions of times more than what you think it should because of the sizes. So this is a lot of energy. 17.7 mega electron volts of energy was created from the mass that was lost. Question, Rowan? You look unhappy with this.
I don't know what's happening.
I can go back. Are you happy when I put in my MC squared formula? Which I got this as the energy in joules. I just converted it into electron volts. It was something like 17 mega electron volts. But that's how many joules it is. Okay. Yeah? Question?
Is M the total mass?
No, the M is the missing mass. So if you were to calculate the mass on the left-hand side, it would be bigger than the mass on the right-hand side. Yes? Be careful, please.
Yeah.
The M is how much of a difference there is between the left and the right. Yeah? Okay, continue? Yes? Alright. The left and the right are different masses. You didn't get this? What did you get?
1.75 into the power.
Oh, it sounds like 50. Ah, no, you made a mistake, I think. What did you use for U? The U, what did you use? Ah, this is the problem. Alright, continuing. You need to get the value of U. You missed that. It was in the first slide. Yeah. Okay, continuing. This is the mass of a proton. Exactly. 1.007276 AMU. This is the mass of a neutron. 1.008665. When you have two masses, two protons and two neutrons together, what does that make? Two protons and two neutrons, what's that?
Or four...
What's it called? What do you get? Two protons and two neutrons, what does that make?
Helium.
Helium. And also, two protons, two neutrons and no electrons is called a what? Alpha particle. A helium-4, an alpha particle, if there's no electrons.
Yeah.
Okay. Now, the mass of two protons of two neutrons is less than what you expect it to be. For example, this is a proton, this is a proton, this is a neutron, and this is a neutron. So this is what we think an alpha particle should be. It should be 4.031882. Okay? But if you actually calculate the mass of an alpha particle, it's in fact only 4.002. So 0.02928 AMU is missing. Now think about that. You have two protons, you have two neutrons, You stick them together to make an alpha, and now the mass is less. You know, it's like if I said, I have this, I put it together with this, and now the mass is lower. That's what you're saying has happened. So now the real question is, this mass defect, this missing mass, where did it go?
Binding energy.
And what the heck does that mean?
This binding energy, like,
Yeah?
to bind them, they need energy.
Really? And what does to bind them mean?
Bind, you know, they are not opposite charge.
Yes?
So this is 0
Yes?
plus 2.
Yes?
They need something to bind.
Good. Very good. Very good. Correct. So, proton is positive, and the other proton is positive. So, according to Coulomb, what happens when you bring two positive charges close together? They repel. So then, if I bring them close enough together, at a certain point they go click and they stick together. Now, you might say that shouldn't happen if you think about it, because if they're both positive, they should separate. So how can they click together to make helium? Well, what has happened is some of the mass in the proton has been converted into an energy to hold the two of them together. And this energy and this sticking together is stronger than the force to try and separate them. In fact, we talked about this. This is called the nuclear force. So the nuclear force gets its energy to keep them together from the mass of the proton and the neutron. It steals some of the mass of the proton and the neutron and converts it into energy to keep the two of them stuck together. Okay? So this missing mass, called the mass defect, is not missing, but has been converted into a binding energy to stick the two protons together. It's also the same, like, why should a proton stick to a neutron if it's not charged? Again, the binding energy. Okay. Do you need binding energy to keep the electron around the proton? No, because they're opposite charges, they can stick together like this. Yeah. So, the definition is the binding energy of an atom is the energy required to hold the nucleus together. This energy E, you can calculate it using a formula. What formula do you think that is? Yeah. Where M is the mass defect, that's the apparent loss of mass when they combine. This is also the energy you need to separate them. Okay, so if I have two protons stuck together and I want to pull them apart, how much energy do I need to pull these two protons apart? The same energy, the binding energy.
Where do we call the energy?
Huh?
Is the first sentence enough?
And the formula.
The word is so confusing. Nuclear.
Wookie, it gets more confusing.
Nuclear.
Yeah,
It's so confusing.
very confusing. Doesn't make any sense, you know? Neutron, nucleus,
Nucleus.
nuke. What else? Okay, did you write the first sentence? The binding energy is the energy required to hold the nucleus together. Yeah. Now, this, you remember we said radiation is the release of alpha, beta, and gamma.
Yep.
Now, what is the force that pushes this out? I think we said it's the weak nuclear force, isn't it? And the force that holds the atom together is the strong nuclear force, or the binding energy. So the reason an atom falls apart is the binding energy is just about enough to keep together, but not quite. So the weak nuclear force is able to push the atoms out because it's slightly stronger than the binding energy to keep it together. Okay, so anyways, the binding energy is how much energy you need to split the atom. So some atoms are harder to split open than others. Okay. Continue? Yeah. So in an earlier lecture we saw that the weak nuclear force is trying to push apart the nucleus, but Newton tells us the atom is not decaying, that the net force must be zero. So there has to be something keeping it together, which is the binding energy, which is actually called the strong nuclear force. So the binding energy and the strong nuclear force are kind of the same thing. It's the thing that tries to hold the protons together with the neutrons. Okay. So you remember the weak nuclear force, there was three properties of it. Firstly, it's weak. Secondly, it's inside the nucleus. It's a repulsive force, and it operates off of a distance of like 10 to the minus 14 or something like that, isn't it? Yeah. Anyways, what do you think the strong nuclear force is?
Strong.
Good. Wow.
Inside the nuclear.
Good.
It's force.
Attractive or repulsive? Attractive because it tries to hold it together, and it operates off of a short distance. It's a strong, attractive force which acts in the nucleus over a very short range, 10 to the minus 15. It's the force responsible for binding between protons and neutrons.
Is this related to the Big Bang Theory?
Yeah, it is. Because whenever you're talking about a scale that's so small and energy so big, it's related to this.
Oh, what do you mean the nucleus over at atom over at atom?
Have I got a mistake here?
No, what do you mean?
Oh, that should be an atom. Should be AN instead of AT.
Yeah.
It's called a typing mistake. A typo.
That's confusing.
I'm sorry if you thought I was perfect. I'm not. So if you want to stick two protons together, it's actually quite difficult because first they're trying to separate as you get them closer. But if you can get it down to this distance apart, if you can get them 10 to the minus 15 meters together, then all of a sudden this strong force is able to grab it and pull it in. But it needs to be very, very close before it can pull it in. Very, very close. That's very difficult to do. Very difficult to do. Yeah.
They not stick like this, just maintain the short length.
No, they stick together.
Like this.
Yeah. But they have to be very, very close before they stick.
You mean it's hard to.
It's hard to get them close because they want to repel. You know? Okay. Continue? Yeah? So what is the binding energy for helium? So first we need to work out how much mass is missing. Then we need to convert that into energy. Now I actually did that calculation earlier, but let's just recalculate it. So the helium is 4.002. That's what it is. But what it should be 2 protons, right? Minus 2, I'll put it like this. Minus, so that's what it is, and this is what we think it should be. 2 protons plus, plus 2 neutrons. Have I got it backwards?
Yeah.
Yeah, sorry, you're right. I have it backwards. Thank you. That's what it should be, 2 protons plus 2 neutrons. But this is what it actually is. So the difference is small. It's this many AMUs. That's how much is missing. Let's convert this into energy. So if I multiply this by, what number, I'm sorry? 17. And the C?
Is 27.
28. 28. Alright, so what's the energy? It's this. Now because this is so small, we usually use electron volts. It's very normal. So let's just convert that into electron volts. Alright. That's mega electron volts. 27 mega electron volts is the binding energy here. That's how much energy is used to keep the atom together. So, that also means that's how much energy you would need to separate the atom, to disassemble it. Now, that's a lot of energy for a little atom, 27 mega electron volts. Okay. Right, so can you write that, or could you write that down? I can go back if you need to, but I think you all get the idea. 2 protons plus 2 neutrons minus what it is gives us how much is missing.
MC squared must be
In the formula calculation, yeah, should be. Okay. Okie dokie. Yeah. Okie dokie, you got that?
Yeah.
So anyways, if you want the final answer, it was, oh, where's it gone? Oh well, I don't remember what we said. That's it. Can I go back? Oh, there we go. 27.3 mega electron volts. Okay, continue. So, this question now is the same, but I just added an extra part. What is the binding energy per nucleon? So, that energy I got here,
Divided by 2.
no, divided by 4.
For nuclear.
Yeah, there's 4 nucleon.
What is nuclear? Nuclear.
Proton and neutron.
Ah, yeah.
Yeah. Now, this energy, that's how much energy it is to hold that atom together. But really what's more important is how much energy is that per nucleon. Okay? So for example, if you have 10 protons being held together and 2 protons being held together, you know of course it needs more energy to hold the 10 together. Obviously it's bigger. So what really is more interesting to know is how much energy that is per nucleon, per proton and neutron. So just simply divide this by 4. And it's, oh, that's not right. No. What number did I get? 27.3, okay. 27.3 divided by 4, that is 6.825 mega electron volts per nucleon.
Is it right?
What do you mean, is it right? I hope it's right.
Why divided by 4?
Because you have 4 nucleons, 2 protons and 2 neutrons.
This is 2 molecules, 2 atoms of helium. the energy.
Yeah, but what's in the nucleus?
No, I mean, you can use this equation. It's true. Why is not true? You're right.
Okay. Continue? Yeah. Okay. So next. What I have here, I'll try and draw it for you if you can't quite see. I'll just explain it here. Oops. Hold on. What unit? Mega electron volt. So this is the binding energy per nucleon in mega electron volts. And then, what letter do we use for the mass number?
A.
Is it Z? No, it's A.
Z. Z.
Is it Z for the
Z.
mass number?
Mass number Z.
Yeah.
Yes.
Okay. Z, which is the mass number.
Yeah.
So just I'll write Z here. Okay. Now, what's the first thing? A proton or hydrogen 1. Okay. That doesn't really have any binding energy, does it? Because there's only one of it. So the binding energy, I suppose you could maybe say is 0. No binding energy is required. Right. The next thing, hydrogen 2. That's 2 protons. You look at the binding energy. Okay. It'll be a little bit more. In fact, all the way at the end here, I think, is uranium 238 or something really large like that. As you move up the number of mass units, you'll notice that the binding energy actually increases. It takes more energy per nucleon to hold the atom together. Now you might say, oh well, that's not really surprising, because as it gets bigger, it's harder to hold it together, so you need more energy per nucleon. But then something strange happens. It reaches a maximum and then it starts to decrease down. Okay, that's what this graph is. In fact, this point up the top here, this is actually, if you were to look at it, it's actually lead.
PB?
PB, yeah. So what's very interesting is it gets harder and harder to put the atom together, and the hardest one to put together that needs the most energy is lead. So this means lead is the most stable. It has the most energy keeping it together. So it means it's the hardest one to pull apart and to separate. So lead is the most stable of all the possibilities you have. It needs the most energy per nucleon. This region of the graph is called fission, and this region is fusion. And actually, we'll look at this in another lesson, the meaning of this, but just they're the names of the two parts of the graph. Most stable.
In high school, they say iron.
Iron. Well, I think
They are friends.
yeah, they're like I'm being a bit too precise. It's actually a couple of things, really. Yes, I'm sorry, Shamsa. Actually, you're right. That's kind of.
P, iron.
I'm totally wrong. You're right. It's iron, not lead. Thank you for correcting me. Although I think right beside it is what number? What number is lead? Do we have our periodic table?
20. What's that?
Do you have your periodic table?
No.
You have it?
20.
Somebody is going to give it to me.
PB is like
Quiet.
PB. I put it first. 20 something.
272.
207? Are you sure?
82.
Okay. 82, alright. Where is I can't see it on this one.
Yeah, there.
Yeah. I didn't quite draw my graph right. It's actually quite flat up the top here. So, iron is the most stable. But there are other things which are kind of similar. Like, can you see here copper? Cu? It's practically the same. Okay. Lead is going to be somewhere up here. I can't see. What the heck is that one? Cl? Yeah. Anyway, for the exam, they don't, when they ask you to draw this graph, which they asked the students in September to do, they don't actually ask you to label any of the atoms on it. What they ask you to draw on the graph is the x-axis you need to have correct, the y-axis you need to have correct, the shape you need to have correct, and you need to have the correct name here and here. They don't expect you to know any of the atoms on this, on the graph, so you don't even need to know this. I mean, I'm not saying forget it, but just you don't need to know it.
If the graph goes like,
Where is the A?
where is the,
Oh, there's a bit of a spike here, but again, for the exam, they want the general shape, which is that it goes up to a peak and comes down. They're not expecting students to know that it has a spike here. Now, if you do draw a spike, fine, I'm not going to take any marks away from you, but I'm just saying the minimum they expect in the exam for full marks is a sort of quadratic shape like this.
Why in the why is this A? Why the bottom is A? New number of nucleons.
You told me the mass number was Z.
I said.
Is it A?
I don't know.
You do chemistry.
It's Z. Is it Z, right?
Ah, for goodness sake, Wookie.
I don't know.
Is I use that.
But I gave it to you and I forgot and I'm hungry. What is it in chemistry? What are you using chemistry for the mass number?
Mass number is the top one.
Yes?
Isn't it A?
Well, it must be A because that's what it is on this graph, so I'm going to believe them.
Yeah.
Thank you for clarifying that.
Is it A?
It is definitely A.
Okay, thank you. What's Z?
Anyways, in the exam, if you forget, you can just simply write mass number. That's fine.
Or nucleon number.
Or nucleon number, yes. But not neutron number.
Slash mega electron volt.
Yeah. Yeah. Because that's the unit that's used.
You mean for A?
For the binding energy, it's common to use mega electron volts. Yeah.
And what is how on top?
Iron. Yeah. Okay. Continue? Yep. Well, that was actually the last thing here. Let's have a look. There are your questions now. Just before I finish that here, we'll have a lesson where we talk about fusion and fission, but just to give you a basic definition, fusion, this part of the graph means it's these elements are a little bit easier to stick together, and fission means these elements are a little bit easier to separate, to pull apart. Now the reason for that, you might say that doesn't quite make sense, because if you look here, the energy per nucleon here and here is the same. So you might say, well, doesn't that mean that this element and this element, they both require the same energy? So aren't they equally easy to both put together and separate? Well, not quite, because the difference is, although you need the same energy per nucleon, this element is bigger. And of course, it's harder to put many things together to form an atom. Although here, if there's less protons to stick together, it's easier to put that together. You know, so although the energy is the same, practically, from a practical point of view, if you have like 2 protons, it's easier to stick 2 protons together than 100 protons, even though the energy might be the same. But if you have 100 protons, which is easier to separate? Something which is 100 protons big or something that's 2 protons big? Well, something that's 100 protons big, it's easier to split this, even though it's the same energy. So that's why this region is called fusion and this one's called fission. Fusion means it's easier to stick the elements together to form, and this one it's easier to separate, even though the energy is the same. It's because of how many you have, makes it easier or more difficult. Yeah. So if you want as a simple little definition, fusion kind of means like stick, and then fission means like break, separate, pull apart. This comes from a verb in English called fuse. Do you know this verb in English?
Fuse.
Yeah, what does it mean as a verb? Yeah, it's a sort of combining, but in a very, very special way. It's like a welding, isn't it? Yeah, you like melt 2 things together so they form a new single piece. That's kind of what's happening here. You have 2 protons, which are 2 separate atoms, and you stick them together to form a new atom. So you fuse them together. Okay. Let's have a look at the homework questions. So, again, this would be a normal exam question, section A and section B. So example here, question 1 would be like an A question and 2 would be like a B question. But it's nice because you're only using one formula. This whole lesson is just the one formula, E equals mc squared, and that's it. Okay. So I'll let you try this for a few minutes. You should be able to do the first question in like 2 minutes, and then we'll start the next lesson. So I'll just stop the video here. To finish this chapter, let's have a look. So we won't get this finished today because I think it's kind of big. So this one's big, this one's small. So 1 class, maybe 2, but we have 1 today. So 1 more, 2, 3, 4. We have a double class on Monday and a double class on Tuesday. So I expect to be finished Tuesday, and we can begin our revision Friday next week. Yeah.